All right, let's go ahead and talk about this very important concept for this unit, core valence electron radius. And if you think about the atom has a positive nucleus. It's surrounded by electrons. Those electrons are attracted to that positive nucleus. Now, something we need to keep in mind is that there's a whole bunch of different electrons in there, and so sometimes electrons can actually interfere with each other in a way that affects their attraction to the nucleus. And so that's something that we want to think about today. So we want to think about how the electrons are attracted to the nucleus. We also want to think about how the other electrons interfere with that as well. So the core valence radius model separates the valence level of electrons from the inner level of electrons. And so when we talk about valence electrons, we're talking about electrons that are on the outermost energy level. And when we start thinking about different properties of elements and different trends that occur on the periodic table, we want to think about them in terms of the valence electrons, all right? The inner electrons are anything that's underneath the valence electrons. Now, something we want to talk about is we want to talk about how the electron, again, when we're talking about how the electron is attracted to the nucleus, we want to think about what is the charge that the electron is sensing from the nucleus. Now, if you have an element that has 7 protons and there's 1 electron around there, that electron is attracted to those 7 protons. However, the reality is that the inner electrons can actually block the nucleus partly from the valence electron. And so what we do is we need to determine this thing called core charge or effective nuclear charge. And so to determine the effective nuclear charge on an electron, and again, we typically are talking about the electrons in the valence level, the outermost energy level. What you want to do is you want to subtract the number of inner electrons from the number of protons in the nucleus. And so we're going to look at an example of this in a moment. But essentially, to figure out the true charge that an electron feels from the nucleus, you have to subtract the inner electrons from the protons. And so effective nuclear charge is also referred to as effective core charge. So it's something that we will talk when we're talking about these things, we'll refer to it as that. Now, the valence level, again, is the outermost energy level and is what determines how atoms react chemically. And the atomic radius of an atom tells you the distance from the center of the nucleus to the outer edge of the electron cloud. And something to keep in mind is that valence electrons are in the outer edge of the electron cloud. Now, the atomic radius is determined in large part by the pool of the positive charges in the nucleus and the number of main energy levels. And so we'll talk about this as we go when we do the practice problem. So again, atomic radius is going to largely be determined by that nuclear charge in the middle. And the energy of attraction or repulsion when the charges are the same is governed by Coulomb's law. And so just to remind you what Coulomb's law states, if you have 2 charges, let's say a positive and a negative charge, the force of attraction that's between them is dependent upon 2 things. It's dependent upon the distance. So the closer those 2 charges are, the stronger the force of attraction. Let's think about how electrons are attracted to protons. So if an electron is close to a proton, there's going to be a stronger force of attraction. And the other one is the amount of charge. So if we have an electron and there's a nucleus that has a lot of protons, that electron will be attracted to more protons than fewer protons. However, we'll see how distance and inner electrons can interfere with that. As the effective core charge increases across the periodic table, the force on the valence electrons increases as well. And so we're going to learn that as you go across the periodic table, the force of attraction on valence electrons will increase, resulting in a stronger force of attraction to the valence electrons. Now, what I'll say is as you go down the periodic table, that force of attraction decreases, and we'll see why that is in a little bit. And as the distance over which the effective core charge must pull increases, again, that's as you add energy levels, you're increasing the distance that the effective nuclear charge has to act on that electron. The force on those valence electrons decreases as well. So as you add more energy levels, the force of attraction to that valence electron decreases. And so the resulting model simplifies the depiction of the atom and focuses on the valence electrons. And again, it's the valence electrons that mostly determine how atoms will chemically behave. And so let's go ahead and take a look at this sort of model here to kind of help us understand this concept. And what we're going to do is we're going to look at the valence electrons of magnesium here. And if you take a look, here is this valence electron. We'll talk about this valence electron. Now, if you look at the center here, the center has 12 protons. Now, what ends up happening is that you'll see we have on this first energy level 2 electrons, and on this second energy level we have 8 electrons. And those electrons aren't sitting there, they're actually going around the nucleus. They're not stationary, so they're going around. And so what ends up happening is these electrons sort of shield the nucleus. So we have 12 protons in the center here, so we have 12 protons. But
underneath this electron here, there's actually 10 electrons. So there's 10 electrons that are underneath this valence electron. And so because there's 10 electrons underneath that, what we would do is subtract those from the 12, which we would end up getting a 2. So even though there's 12 electrons here, even though there's 12 protons, this electron does not sense the 12 protons. It actually only senses 2 of them because those 10 inner electrons are blocking some of that charge. And so you've got your outermost energy level, you've got your inner electrons. Those inner electrons block the nucleus, and so the effective charge that those outer electrons experience are less. And so you can see there's a nice little divide there, and what ends up happening is the nucleus has a 2+ charge that the outer electrons experience. Now, what I will say is those inner electrons do not experience a 2+, they actually experience more than the 2+, because those inner electrons don't have anything underneath them blocking the nucleus from them experiencing it. So we're going to go ahead and go through some practice problems, and we're going to sort of put all of these concepts together. Again, the key thing here is that electrons are attracted to the nucleus. The outer electrons are going to be shielded from the nucleus by the inner electrons. So the inner electrons are shielding the nucleus from the outer ones. So the outer ones, even though there might be 20 protons in the center, the outer electron is not going to have the same attraction as if there's 20 electrons. It's going to be sort of blocked or mitigated by the inner electrons. So we're going to go ahead and do some practice problems going over this, and you'll see that there's actually a pattern that occurs on the periodic table when it comes to this core charge. So watch that guided practice problem video. Come to class with questions. You guys have a great day.